expression for capacitance of parallel plate capacitor when dielectric medium is present. In the last class we have discussed about if there is no dielectric between the two plates of a capacitor. That means in between the two plates if there is air or vacuum, then what is the expression for capacitance that we have discussed in the last class. Suppose if we insert a dielectric in between the two plates of a capacitor, then what is the expression for capacitance? For that, so initially let us consider a parallel plate capacitor with air between the two plates. Okay, air or vacuum between the two plates. So here, when air is present in between the two plates of a capacitor, let us consider the surface charge density of each plate is sigma, and the electric field between the two plates of a capacitor as E0. We have derived the expression for electric field between the two plates of the capacitor. So in the last class as E is equal to sigma by epsilon naught. Here I have taken the electric field E0. So E0 is equal to sigma by epsilon naught. Let us take D be the distance of separation between the two plates and A as the area of each plate. Okay. So each plate. Okay. And V0 is the potential difference between the two plates of the capacitor. Suppose when dielectric is inserted between these two plates of the capacitor, when dielectric is inserted in between the two plates of a capacitor, due to this field E0, this dielectric gets polarized and some electric field will be induced in the dielectric field. So let us take that induced electric field as ED. Therefore, the net electric field when dielectric is inserted, so this E0, that is the applied electric field, is in this direction. That means before inserting the dielectric, the electric field E0 is in this direction. So after the application of, after inserting the dielectric, the electric field gets induced and that is acting in this direction. Okay. So the net electric field, so due to this whole arrangement is given by E is equal to, since these two are in opposite direction, we can write the net electric field as E0 minus ED. Let us consider the induced electric field ED due to the dielectric polarization as, so in between the two plates of the capacitor, the induced electric field due to dielectric polarization is given by sigma by epsilon naught. Here, this electric field is developed due to induced dipole. Therefore, surface charge density of the dielectric is given by sigma d by epsilon. Now, substitute these two values in this equation. So we write E is equal to E0 means sigma by epsilon naught minus ED means sigma d by epsilon naught. Now we can take this E0 as LCM. Therefore, E can be written as, we write sigma minus sigma d. Okay. The surface charge density before inserting the dielectric minus surface charge density of the dielectric. This two difference, that is sigma minus sigma d, is directly proportional to, since the surface charge density of the dielectric slab depends upon the surface charge density of the plates of the capacitor before inserting the dielectric. Therefore, we can write sigma minus sigma d is directly proportional to sigma. Now remove this proportionality symbol and add a constant. Let us take that constant as k. So we are adding a constant, that is 1 by k. Because when you insert the dielectric slab, the overall surface charge density decreases. In order to represent that, we have taken the constant in the denominator. Here, this constant k is called as a dielectric constant. We call this as a dielectric constant. Okay. And this dielectric constant is equal to 1 for air or vacuum. It is equal to 1 for air or vacuum, and for other than air or vacuum, for any other medium, the value of K is always equal to, it is always greater than 1. Any other dielectric medium, K is always greater than 1. Now, substitute this value sigma minus sigma d as sigma by K in this equation. So, E is equal to sigma minus sigma d value is sigma by K. So, we write sigma by K. So, already in the denominator epsilon naught is present. We know the surface charge density is the ratio of charge to area of the conductor. Now, substitute this value to this equation. So, we can write E is equal to Q by A epsilon naught K. In place of sigma, I have written Q by A. And we know the relation between the electric field and the potential difference as E is equal to V by D. That I have discussed in the last class itself, previous derivation. Now substitute this value here. So we can write V by D is equal to Q by A epsilon naught into K. Now cross multiply these two. This goes here and this comes here. Okay. So we can write, so A epsilon naught K by D is equal to Q by V. Right. Q by V, that we already know, ratio of charge to the potential difference between the plates of the capacitor is capacitance. So in place of Q by V, we can write C. So C is equal to A epsilon naught K divided by D. This is the expression for capacitance of a parallel plate capacitor when dielectric medium is present in between the two plates. That is A epsilon naught K by D. Now let us consider. So suppose if there is no dielectric medium between the two plates of a capacitor, then the capacitor is given by A epsilon naught by D, where A is the area of each plate of the capacitor, D is the distance of separation between the two plates, and epsilon naught is the permittivity of free space. Epsilon naught is permittivity of free space. Okay. Now here K into epsilon naught can be called as epsilon, and we call this as a absolute permittivity. We call epsilon as a absolute permittivity of the dielectric medium. Okay, absolute permittivity of the dielectric medium. Epsilon naught is the permittivity of free space, and K is called as a dielectric constant. And this dielectric constant can also be written as, now take this epsilon naught here, epsilon by epsilon naught. That means the ratio of absolute permittivity of the dielectric medium to the permittivity of free space is called as a dielectric constant, and this dielectric constant has no SI unit. It has no SI unit. Okay. And this dielectric constant K can also be called as the relative permittivity of the medium. It can also be called as the relative permittivity of the dielectric medium. Okay, and this dielectric constant value is equal to 1 for A and greater than 1 for any other medium. Okay, so now suppose if we consider the capacitance of a parallel plate capacitor when air is present in between the two plates or vacuum is present, that means air parallel plate air capacitor. Okay, then capacitance is given by A epsilon naught by D. Now take this as C naught, that means without inserting the dielectric. After inserting the dielectric, it becomes A epsilon naught by epsilon naught K by D. Now here in place of A epsilon naught by D, we can introduce C naught. Therefore C can be written as C naught into K. Now K can be written as C by, now take this C naught here, C naught. Now the dielectric constant can also be defined as the ratio of capacitance of a parallel plate capacitor when dielectric medium is present between the two plates to the capacitance of parallel plate capacitor when the medium between the two plates is air or vacuum. Okay, ratio of capacitance of a parallel plate capacitor when dielectric is present in between the two plates to the capacitance of a parallel plate capacitor when air is present between the two plates. Air or vacuum is present in between the two plates of a capacitor. Okay. So this is about the expression for capacitance in case of a parallel plate capacitor without dielectric and with dielectric. Now, let me move on to discuss about combination of capacitors. So, here, what is meant by combination of capacitors and what is equivalent capacitor and what is equivalent capacitance, that we have to discuss. See, in order to get the required value of capacitance, we can join two or more capacitors together. Okay, so like this. So we can join two or more capacitors like this, and also we can join two or more capacitors like this in order to get the required value. For example, I require some 10 microfarad capacitor, but I have 2 and 3 5 microfarad capacitor, but I have 2 microfarad capacitor and 3 microfarad. So then I have to join them to get the 5 microfarad capacitor. Okay. So that means in order to get the required value of capacitance of a capacitor, we can join the capacitors, 2 or more capacitors. We call that as a combination of capacitors. Okay. So in this there are two types of combination. One is series combination and other one is parallel combination. One is series combination and other one is parallel combination. Okay. So now, what is meant by equivalent capacitance and what is meant by equivalent capacitor? Suppose, so if I combine these three capacitors, for example, 1 microfarad, 2 microfarad and 3 microfarad capacitance. Okay, 3 capacitors each are having the capacitance like this. By combining all these, if I get some 6 microfarad, if I have a single capacitor of 6 microfarad, so that is equivalent to combination. What is equivalent capacitor? A single capacitor that can produce the same effect as that of 2 or more capacitors in combination. Okay, that means if a single capacitor can produce the same effect as that produced by the 2 or more capacitor in together, that is called as a equivalent capacitor, and capacitance of that capacitor is called as equivalent capacitance. Did you got this? What is meant by series combination? Okay, series combination means if 2 or more capacitors are connected end to end, means one end to other end, one end to other end, like this, one end to the next end. If 2 or more capacitors are connected end to end, so that the charge on each capacitor is same. Charge on each capacitor is same, but the potential difference is different. Okay, it's called as a series combination. Series combination is the combination in which 2 or more capacitors are connected end to end, so that charge on each capacitor is same but not the potential difference. Then what about the potential difference? The potential difference is equal to the potential difference across the equivalent capacitor is always equal to sum of the potential difference between the individual capacitors. Now let me move on to discuss about the capacitance of a equivalent capacitor in series combination. Expression for capacitance in series combination. For that I have considered two capacitors having capacitance C1 and C2. And the charge on each capacitor is Q. And the potential across the capacitor C1 is V1 and potential difference across the capacitor C2 is V2. And potential difference across the equivalent capacitor is Vs and equivalent capacitance is Cs. According to the definition of series combination, I have told you it is the combination in which two or more capacitors are connected end to end, so the charge on each capacitor is same but not the potential difference. That means potential difference across the combination is always equal to sum of the potential difference across the individual capacitors. So now take the potential difference across the equivalent capacitor is equal to the sum of the potential difference across the individual capacitors, that is Vs is equal to V1 plus V2, but charge on each capacitor and that of equivalent capacitor is same. Okay. We know capacitance is the ratio of charge to the potential difference. So, V can be written as Q by C. Therefore, Vs, potential across the equivalent capacitance is Q by Cs. Here charge remains same. Okay, charge of C1, C2 and Cs is all Q. And in the same way, potential difference across the first capacitor is Q by C1. And potential difference across the second capacitor is charge is Q and capacitance is C2. Now substitute these values in this equation. So we get Vs is equal to, Vs means Q by Cs is equal to, V1 means Q by C1 plus V2 means Q by C2. Here I can take Q as common. So if you take Q as common, then 1 by C1 plus 1 by C2. This Q and Q gets cancelled. Therefore 1 by Cs is equal to 1 by C1 plus 1 by C2. This is the expression for capacitance, equivalent capacitance of a capacitor in series combination. That is, the reciprocal of the equivalent capacitance in series combination is always equal to the sum of the reciprocals of the capacitors of the each and every capacitor in that combination. Okay. Now take, so if we consider the two capacitors, then the expression for equivalent capacitance will be 1 by Cs is equal to 1 by C1 plus 1 by C2. Okay. Then this can also be written as, now see, 1 by Cs can be written as, now take the LCM. So we get C1, C2. C2 into 1 is C2 plus C1 into 1 is C1. So we write 1 by Cs is equal to, now 1 by Cs is equal to C1 plus C2 divided by C1 C2. Now take the reciprocal. So Cs is equal to C1 C2 divided by C1 plus C2. This is the simplified form of the expression for capacitance, equivalent capacitance in series combination, that is Cs is equal to C1 C2 divided by C1 plus C2. Now suppose if I use more than two capacitors, like this is one capacitor, this is one, like this, if I combine n number of capacitors, then the expression for the equivalent capacitance is given by 1 by Cs is equal to 1 by C1 plus 1 by C2, this is second conductor, capacitor, and third one 1 by C3. This goes on up to the nth capacitor. That is 1 by Cs is equal to 1 by C1 plus 1 by C2 plus 1 by C3 plus up to 1 by Cn. We are adding. The reciprocals of capacitance are added to get the reciprocal of equivalent capacitance when n number of capacitors are joined together end to end. That means in series combination. Suppose all these n number of capacitors are identical. Identical capacitor means all the capacitors are having the same capacitance. That means if C1 capacitance of first capacitor is equal to the second and equal to third, like this. Let us take all these equal to C. Okay. If identical capacitors are connected in series combination, then we write the combination as 1 by Cs. That is, so capacitance in series combination, reciprocal of the capacitance in series combination of identical capacitors is given by 1 by C1 value is C plus 1 by C2 value is C. Up to N we have to add. That means we are adding 1 by C n time. So we write n into 1 by C. That is n by C. Now take the reciprocal. So Cs is equal to C by n. Suppose if n identical capacitors are joined together n to n, then the equivalent capacitance is equal to C by n.